Hey everyone, welcome to our materials discovery event with artificial intelligence, of course. And our first speaker today from Germany, capital in Berlin, is Seyed Mohamad Moosavi. He is a scientist at the Freie Universität Berlin, and he will share some blueprints for automated material discovery today with us. And with that, Seyed, stage is yours.
Thank you very much, Christoph, and also Hasha for the invitation. Good afternoon, good morning, everybody. It's great pleasure to be here today to discuss with you our research on material discovery using artificial intelligence. So, from our perspective in chemical sciences, when we think about multi-scale design and discovery, we are often given a problem that has a multi-scale nature. Whether it is design of a catalyst or design of an adsorbent, we come up with a conceptual design. So let's say we want to do a adsorption-based separation. And for this conceptual design, we end up with some indicators, performance indicators, that we try to optimize by searching the chemical space available to us. So we would like to explore all possible materials, for example, that end up giving us the best performance. And in my talk, in the next 15 minutes, I will talk about two examples of how AI is helping us to do this process in a much more efficient way by giving two examples from with designing materials for carbon capture applications and another example about material synthesis. While the methodologies are probably general and applicable to other fields, my examples will be from the field of metal organic frameworks. These are porous structures, Lego-like material made from assembly of these building blocks on a 3D network. And as you can see, they are porous structures. They have high surface area and also come with very good chemical tunability. And because of these, they are considered for a wide range of applications like gas separation or energy storage, catalysis, sensing, and drug delivery that I listed here. And of course, because of this scientific excitement about them and wide applicability, the number of available MOFs at the moment is exploding. As you can see that I'm showing the number of reported MOFs and other materials in the Cambridge Structural Database. Now we have over 500,000 of them available, either experimentally made or computationally predicted. And the research in academia in the past, let's say 5 years using AI has made great progress for using these methodologies to explore these materials for a wide range of applications. I have listed a few of the remarkable progress, and you will hear more about these through the talks today as well. So the first example of my talk is about carbon capture materials. And this is an example where really you see the multi-scale nature of problems that we try to solve. We start from quantum mechanic level, atomistic scale, all the way up to the process engineering. And this is when you try to test the material for a carbon capture application, and you see that one of the material properties that is coming into the picture is the heat capacity of the material. Heat capacity is related to the lattice vibration. You can see on the picture things are vibrating. And this is a property of the material that traditionally or conventionally assumed to be a constant for all the materials that were considered for carbon capture application. But we argue that this is not really true because this study came out and showed that, in fact, using the actual value of the heat capacity can be very important. So I'm showing a plot that is a parity plot. We want to be on this side of the map. We would like to have low energy penalty, high productivity for each material that are tested for this pressure swing adsorption separation, separating carbon, CO2